Hello, for this sixth section in strength of material interview preparation. So let's talk about the bending equation and its assumption and why do we need it and why do we use it. So basically, if we have a beam something like this which is simply supported and we have a force applied, point loads applied here, we can see that the beam will bend like this. Okay, so the beam will bend. It will you will see that due to the bending stress there will be a tension stress and compression stress here, so the length will be L plus delta L and here L minus delta L because the length is decreasing. So this center axis is called the uh, neutral axis. This is the neutral axis. This is the length at which this is the axis at which the length doesn't change. Okay, so this is the cross section. You can see that the cross section, the stress is changing. This is the compression stress, this is the tensile stress. So this changes linearly like this. So as you can see from here, from this cross section, we can find the moment of inertia as BD cube by 12. Okay, and this is the maximum. This is the distance from the neutral axis at which the stress is highest, compression or tensile. This is the distance which notifies that. So from the bending equation is defined something like this: m by I is equal to sigma by y is equal to E by R. So sigma is the bending stress, E is elasticity, R is the radius of curvature, y is the length to the maximum stress, and m is the resisting bending moment, I is the moment of inertia. Okay, so loading at, so we have if the question is asked like tell us the loading condition at which the radius of curvature is same everywhere. So in such cases that where the beam is loaded with only the moment. So in that case the BDM diagram, the bending moment diagram, will have the only moment as a rectangular shape. At that case, from this relation we can find that R is equal to EI by M. EI is basically constant for the given material and M is constant because it is same all over the beam. So at this case the R is constant, and at that case the radius of curvature will be same for the whole body. Okay, so what are the assumptions in this bending equation? So first assumption is the material is elastic, homogeneous and isotropic. Isotropic means all the properties are same on all direction. Homogeneous means the chemical composition is same everywhere, and the material is elastic. So that means the elasticity should be same everywhere in the whole material, and the transverse section is plane. That means this, if this cutoff section, if you slice it, the sections should be plane, it should not be bent. So in that case only the compression and the tensile stress will be same, and that means the deformation, upper deformation, lower deformation, the deformation will be same on the upper and lower case. Okay, that's why it's the assumption that transverse section should be plane and the beam should be straight before the bending. Okay, so the uses, why do we need this bending equation? Because it is used to calculate the bending stress from the moment, bending moment, resting bending moment, and moment of inertia. From this we can get the bending stress. From this we can analyze the failure condition. So what is neutral axis? So after bending in neutral axis, the length will be same. The length doesn't change along the neutral axis. So in the neutral axis, the stress induced is zero always. The stress induced at this point here, it is zero. Okay. So next is, what is cession of modulus and its significance? So we have the bending equation like this. From this we can derive the equation here. So from this section we can find that the resisting bending moment is equal to the maximum stress induced in the body, and this is the Uy is the maximum length taken as the stress is maximum at y max. So from this diagram we can see that this is the y max. Y max means at which the stress is highest, that is y max given. So the cession model is defined as Z is equal to I by E max and M is equal to EY times Z. It means that the point at which the section model is highest, at that point the resisting moment will be higher. For this, for example, if you have a bending beam like this and we apply the force here, in the BDM the moment is highest here at this point. So in that way the slice of this section of the material shows us at which point the resting moment will be highest. For this, for example, you can see this D is higher than this d, that means the z from this calculation, the I and y, the z, the calculation z2, the z2 will be bd square by 6. This z2 will be definitely will be bigger than the z1. Okay, z2 will be bigger than z1. This means the section modulus is higher. If the value of the section modulus is high, that means the beam's resisting moment will be higher. That means it will be much harder for the force to bend this given beam at this section, at this orientation. So in railways we use this I kind of section because the Z3, the section modulus of this section, is much higher than this one. That is why we use this section. So the more the resisting bending moment, the beam won't bend easily, and we want the I section for the same material. For same material, we want this kind of section because it has higher section modulus as well as the higher resisting bending moment. So which section for column do we use? So we choose a square column because the deformation can happen in any way, because if we have a rectangular shape, then the deformation can happen in the lower side. So if you have a square, it may happen in all the direction, and that means it is much good for compressive stress, and the reinforcements are basically applied in the boundaries of the column. Okay, so everywhere in the boundary they are applied. So this is good for the direct compressive stress. So basically in the concrete, so you can see this has a very high compressive stress, good for the shear, high compressive stress you can take, but it's very weak in the tensile stress. So for that we need to enforce this concrete. So the enforcement happens in the bottom because the tensile stress is higher, and that is where the weakness lies. So enforcement happens in the bottom. Okay. So next is the section modulus for circular. So how do we calculate the section modulus for circular section like this? So the I is pi d4 by 64 and y is this. From this we can calculate the section modulus. Okay. So for thin pressure vessels there are two types, spherical and the cylindrical. And cylindrical we say it is a thin given the condition that the thickness is less than d by 15 to d by 20 times. So if this condition is there, that means the cylinder is thin vessel. Okay. So if this is a cylinder and the pressure is inside, that means along the circumference this stress is called hoop stress, and that hoop stress is the major stress, and the calculation of this hoop stress is PD by 2dt, PD by 2t. So we can find this from here, stress times the area, which is the force, and P times the DL. So this is the pressure. So force and force we can find the stress, and the longitudinal stress, which is the second major stress, is basically half of the hoop stress. Okay, so the longitudinal stress will be PD by 4t. Okay, next is the Mohr circle. For this condition the Mohr circle will be like this. The circle will be like this. From this we can find the maximum shear stress. It will be rho 1 sigma 1 minus sigma 2 by 2, that we get as PD by 8t. Okay. Next is, as we can see from the cylinders in which you get the LPG cylinders, they are welded like this, but not like this. There is a circumferential welding, but not longitudinal welding. What is the reason? So we can find the reason from the efficiency of the circumferential and the longitudinal junction. So for example, if we have a cylinder like this and there is a longitudinal cavity, a hollow cavity, so in this case the stress will be higher in the circumferential direction. In circumferential direction the stress will be higher. In that case the hoop stress or the maximum stress will be PD by 2t times the efficiency. This means the stress increases for the major stress. But when we have the circumferential hollow cavity, in that case the longitudinal stress increases, and the longitudinal stress formula is PD by 4t times the efficiency, which is this symbol. So in this case we don't want the major stress to be higher. That is why we take this kind of stress, and for that we will take the circumferential hollow cavity, and this circumferential hollow cavity can be made through the circumferential welding. So we choose circumferential junction or the cavity, and we choose submerged arc welding method for this in circumferential direction. Okay, this is the arc welding method, submerged arc welding method. So we choose this one, not this one. Okay. So next is this strain calculation. So for this case, for the thin vessel cylinder case, so what is the strain calculation? So we have this major minor stress like this. From this we can calculate the strain as sigma 1 minus rho sigma 2. From this, the same formula we can find. And for this circumferential thing, the deformation is through is a radial deformation, and for this it is a linear deformation. And if you want to calculate the volumetric strain from this formula of the cylinder, we can put the log on this formula and then differentiate. We will find that the volumetric difference is equal to twice the radial difference plus the longitudinal strain. Volumetric strain is equal to twice the radial strain plus the longitudinal strain. Okay. Next is for thin shell. As we discussed earlier, that for the thin shell, it's everywhere it is a longitudinal stress. In that case, we will have the body diagram is like this, and the most angular as a point. As the hook stress and longitudinal stress are the same, the major and minor stress will be PD by 40. Okay. Next is the column and strut. What is column and strut? Basically, if you have a beam like this and we have a force like this, the shear force is applied here. But if we have a column, it is only the axial force applied, and the column is something in which the difference between basic column and strut is that the strut is basically long and slender body. So in column only the axial force is applied, and so axial force creates the compressive force, which is compressive vertical force, direct compressive force, and the strength is basically compared with the crushing strength of the material. And the strut is basically a slender body, and only axial compressive loads are applied, and this shows in buckling effect, in which no direct compressive stress are applied here, only buckling effect is there. So types of columns. So basically there are three types: short, long, and medium. In short, only direct compressive stress is applied, that is sigma is equal to F by A, only compressive stress is applied. In long, it is a slender, it is basically strut, it is basically crippling load is applied, and bending stress, we can see the buckling effect. From here we can find the bending stresses, and it is we can find the crippling load from the Euler's formula. And next is the medium kind of column, in which the both direct compressive and the bending stress are applied, and that can be found through the Rankin formula. So in medium column cases, you can see if this is the column, the load is applied. So if this column basically bends like this, as you can see the deformation is outside like this and inner like this. So outside is the tensile stress will be there, and inside the compressive stress will be there, and above this there will be a compressive stress, direct compressive stress, which is this F by A, which will be added to the compressive stress of the bending stress, and minus the PDT, because the compressive stress will get added to the compressive stress. So basically, if they ask for the failure point, so the failure region will be in the inner part, okay, because the stress is very high, so the failure will happen in this region. So next one is the Euler's equation for the slender body, which is for the strut. So the crippling load formula is P is equal to pi square EI by LE square, so equivalent length, which depends on the ending condition. And there are some assumption for the Euler's equation, which is the column is long, that is strut, and only the buckling load or bending stress is found in that body. So the end condition for this equivalent length is basically, if it is hinged, the length is L. If it is fixed, it is L by 2. If it is free, it's 2L. If it is fixed and hinged, it is L by root 2. So as we know that the moment of inertia is equal to A K square, is the area, and this is the radius of gyration. So radius of gyration is K times this. K is equal to this expression, and from this crippling load, you can actually identify the crippling stress as this expression, and this expression is basically the slenderness ratio. Slenderness ratio is equivalent length by K whole square, which should be less than 80. If it is less than 80, only then it will satisfy the Euler equation, Euler condition. Okay. So next one is the Rankin formula. Rankin formula is for the medium column in which direct stress and the bending stress are applied. So the compressive load, safe load, which is called, the expression is this, and this A is basically Rankin's constant, and this is the sigma is the compressive strength. Okay, so this is the formula to be remembered. So next one is the case in which if we have a load something like this, which is we have a circular section beam, and if the load is applied on the edge, so this kind of force will create both bending moment as well as the compressive stress. Okay, the deformation will be something like this. It will create bending stress as well as the bending moment. Okay, what kind of shear stress is induced in the beam? We have discussed earlier. So if you know, if the shear force is applied, so there is the transverse shear stress here and here, and there is a complementary shear stress here. So if you want to calculate the transverse shear stress, it is nothing but F by A, and that is the average shear stress. If you want to calculate the complementary shear stress, we have to little bit we have to work more. So the complementary shear stress is equal to Fa times y mean by Ib. Y mean is basically the distance between the neutral axis to the centroid of this shaded area, and this shaded area is nothing but it is a region at which the shear stress will be higher, it's maximum. So we are analyzing only this shaded area, and y is the distance between this neutral axis to the lower shaded part. So this is the formula. So basically for the rectangular section like this, if this will be the maximum shear stress diagram. So we can see that the average shear stress will be FIA, but the maximum shear stress will be 1.5 times the shear stress. So for the second region, it will be 4 by 3. This is the ratio to be remembered. But if you go to the other sections like this I type, the diagram will be like this, because the greater the distance, the lower will be the shear stress. But when suddenly when